All right, everyone. All right, the all right is never going to stop. I've given up. It's just the world we live in. All math videos will start with all right. We're going to do number 64 in the textbook, which says use a graph of f to sketch a graph of its derivative. These are really good problems. I really like these. So this blue graph up here, this is the function f of x, and we want to graph the derivative. So again, we just estimate a bunch of slopes. The slopes are going to give us the derivative. Let's let f prime of x, right, is the slope of f. So just look at the slope of the blue graph and plot that y value. So notice, right, let's start with the easy ones. The slope of the blue graph is 0 right here because the tangent line's flat. So the slope of the blue graph is 0. So the red graph, which is the slope function, going to have a value of 0 here. Similarly, going to be a value of 0 here. Now in this region, as we're walking along the graph from left to right, are we going uphill or downhill? And we're going uphill. The slope's going to be positive. So we know, I don't know what our slope values are going to be, but I know they're going to have to be positive in this interval. So we can just do some estimates. And it's a little hard because if we look at this box is 1 by 4. This box goes right 1 unit, but up 4 units. So it's a little hard to estimate the slope. But let's do it. Let's estimate the slope like right here. Slope here, actually it kind of goes up 4 and right 1. You look at the slope of this one, right? It kind of goes up 4 and right 1. Not quite 4, but close, maybe like 3. What's the slope right here? Yeah, close to up 3 and right 1. The slope is about 3 right here. In the middle of these 2 points, the biggest it ever gets is about 3. And it kind of connects like this. Now let's just look at some other slopes. Let's look at the slope of the function at 0. It's going to be this tangent line right here. What's the slope of this tangent line? Well, it's about down 1 and right 4. Sorry, down 4 and right 1. The slope's about -4. Let's just look at other tangent lines. Let's just look at a bunch of tangent lines and plot a bunch of points. That's how you do this. Let's look at the slope at -1. So we draw the tangent line and say, what's the slope about right here? Well, it's kind of going down a lot, and then it kind of connects over here. Like if we extended this line. So that's going like down like 10, down 10 and over 1. Slope is about -10 right here. So red is our slope function, so we're going to draw about -10, a little bit smaller than -10, I think. Maybe closer to -12. And we can do it on the other side as well. Like what about at 3? Well, at 3, what does the slope kind of look like right here? Well, we can go right 1, and we go down about 4. Slope is about -4 right here. So plot that on our slope graph. And we can do the same thing at +4. And again, you get a slope around here. The blue function is a cubic. And if you look at a bunch of tangent lines, look at a bunch of slope values, then your slope function, this red function, is actually going to look, it's not a perfect graph, but it looks kind of like a parabola. It's a little wonky here, but that's like a sketch. It doesn't need to be super nice. It should just be a rough sketch that looks like this. Okay, and that's how you approach these sorts of problems. That's the relationship between a function and its slope. Let's do another one. Number 70 in the text. The given limit represents the derivative of the function. Find the function itself. So f prime of x for 70 is the derivative. That's the limit as h goes to 0 of cosine of pi plus h plus 1 over h. And it wants us to find what is f of x. This is a conceptual question asking you, can you relate the definition of the derivative with the function itself? And actually, it doesn't want f of x. It wants f of a. All right. So let's look at what is this equal to? What is the actual definition of the derivative? In generality, it's the limit as h goes to 0 of the function evaluated. Sorry, again, it's really asking about at a point A. It's the function at a plus h minus the function value at a, all divided by h. So really, it just wants you to compare what we have with the definition and try to kind of fill in what's what. So looking at this, right, there's some pretty close correspondence. Specifically, we know that cosine of pi plus h is equal to f of a plus h. And that tells us almost everything we need to know. That tells us the function, and that tells us a, right? It's going to be cosine of pi. So right here, right, f is the function that's cosine. H is h. So a has to be pi. So the function is cosine. A is pi. And f of a is just cosine of pi. I want to reread the problem, make sure that we're answering it correctly. Find f of x and a. Oh, okay. So it didn't necessarily want f of a. It did want f of x and a like this. The function is cosine. That's the function we're taking the derivative of. The point that we're taking the derivative of is at pi. And we should be able to check our answer, right? Plus 1 should equal negative f of a. So what is negative f of a? Should equal plus 1. Well, negative f of a, that's a negative cosine of pi. Cosine of pi, you can think of cosine as the x-coordinate on the unit circle. Pi is 180 degrees. What's the x-coordinate on the unit circle here? Negative 1. Great. That all kind of checks out. $74. Sketch the graph and use the definition of the derivative to show that the function's not differentiable. And I believe I mentioned that you can just do this on Desmos. I don't think I said that you had to copy this down. I don't remember off the top of my head though. So for 74, let's graph these on Desmos. Remember how to graph piecewise functions. 2 square root of x. And we're on this piece between 0 and 1, inclusive on both. So piecewise functions on Desmos, all you have to do is type the domain for that piece in brackets. And the other one is 3x minus 1. And that's for x bigger than 1. So notice this function, let's have this function be the same color. It is one single function. Notice this function's continuous. right? This function's connected. There's no jumps. There's no gaps. This function's continuous, but it's not differentiable. It's sharp at this point. The slope from the left is different from the slope from the right. What is this problem officially asking us? Use the definition of the derivative to show. All right, so graphically, we can see it, but it wants us to look at the definition of the derivative as well. So this function is the piecewise function, 2 times the square root of x, when x is between 0 and 1. And was it 3x plus 1? 3x minus 1. For x being bigger than 1. The definition of the derivative, f prime at 1, is the limit as x approaches 1 of f of x minus f of 1 divided by x minus 1. This is one definition. Remember, there were 2 definitions that we looked at in section 3.1. We can also use the definition with h's if you'd like. But to find this limit as x approaches 1, and I think this is a little easier to see here than the h definition, but both are fine. As x approaches 1, it depends. From the right, we use that piece. From the left, we use that piece. So we really have to look at 2 one-sided limits. The limit as x approaches 1 from the left of this function, and the limit as x approaches 1 from the right of this function. Because these are going to be different. Well, we evaluate them different. They could be the same thing. So from the left, if we're to the left of 1, we have to use that top piece, and our function is just 2 root x. The function value at 1 is always the top piece. When x equals 1, we always use the top piece. It's 2 times the square root of 1. Right? F of 1, regardless of which piece we're looking at, is included in that top domain. So it's 2 times the square root of 1. F of 1 is always equal to 2. And then we'll do the blue one later. The blue one should be a little easier. I didn't give myself enough room because this is a square root limit. So we have to multiply by the conjugate. That's going to be the limit as x approaches 1 from the right, from the left, of 2 root x minus 2 times 2 root x plus 2. And we'll leave the denominator factored. We don't want to cancel. We're multiplying on purpose. This is the limit as x approaches 1 from the left of the first thing squared, which is 4x, minus the second thing squared, because this is the difference of squares formula. Let's just scroll down this time. Let's go off the board. We're writing on the walls now. We've dropped beneath the whiteboard, or the blackboard in this case. And now we factor out a 4. And things are going to cancel, which is great. That gives us the derivative from the left is this limit of just 4 divided by 2 root x plus 2. We can use direct substitution now. Plug in x equals 1, plug that into a calculator, and the slope from the left equals 1. At this point, from the left, this slope is about 1. From the right, let's evaluate the slope too. Well, I don't like the sidelines. Let's get rid of those. From the right, the function was just 3x minus 1, right? Yeah, from the right, it's 3x minus 1. And the function value is still 2. Oh, this limit's much easier. There's a limit as x approaches 1 from the right of just 3x minus 3. And we'll still factor and cancel. I'll go through this a little quickly. Limits, we've been doing limits for a long time now, it feels like. Well, I guess I have been doing limits for a long time. You guys have been doing limits for much shorter than I have, probably. I should hope, anyway. So from the right, the slope is 3. Which makes sense. This is a line. We didn't even need to use the slope formula, the derivative. We know the derivative is slope, and we know the slope of a line, mx plus b, is just that m. The slope of that line is 3. The derivative being 3 should not be a surprise. Well, the derivative is the two-sided limit, but the one-sided limits are different. Right? So one-sided limits are not equal to each other. So f prime of at 1 does not exist. So looked at that, they're not the same. A derivative is just a limit, and a limit only exists if the one-sided limits are the same. Another way of saying that is the slope from the left is not the slope from the right. We got a sharp edge. Now we could change this function. If we made it this function now, this function is differentiable. It starts off with a square root function, and then it becomes a line. The derivative from the left and from the right are both 1. So this different function would be differentiable, but the original function was not. All right, last problem in this video. Let's look at number 78. Did I give you guys a really nasty one here? Determine for which values of x the limit exists but is not continuous, and which values of x the function's continuous but not differentiable. All right, so let's do the first thing first. Where is f not continuous? F is not continuous at x equals. So remember, there's a couple different kinds of discontinuities. It's not continuous at -4. That's a jump discontinuity. The limit from the left is different from the limit from the right. And then it's continuous, 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 continuous. Another jump discontinuity at x equals 2. Continuous, 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 not continuous at x equals 4. It's continuous everywhere other than those points, assuming that this goes on forever. Kind of a boring question for part A. Determine which values the function is continuous and not differentiable. So what values is this function continuous and not differentiable? Differentiability implies continuity, but the other way around is not true. And the answer is going to be no place. Like if we look and say, where does the derivative not exist? The derivative only doesn't exist at -4. Derivative keeps existing. 2, the derivative doesn't exist. And 4, the derivative doesn't exist. So there's actually no places where the function's continuous and not differentiable. Here, they actually do overlap differentiability and continuity. They don't in general, but here they do. So for part B, there's no x values for which this applies. But for like number 79, for example, there are. Number 79, when x equals 2, this function's continuous, but it's not differentiable. When x equals 2, shouldn't have clicked, Jason. When x equals 2, the slope from the left is a positive number, but the slope from the right is a negative number. Slopes from the left and the right are different, which means the derivative, which is the two-sided limit of the slopes, doesn't exist. So for part B, in this one, we'd have x equals 2 be an answer. All right, that's pretty much it. Let me know if you have questions. Have a great day. The sun came out. I hope the sun is out for you. Although it might be night. Although it's summer and, well, who knows when you're watching this video. Bye-bye.